right? One of those was show that a linear function of a Gaussian random variable gives us a Gaussian random variable. Right? That was pretty straightforward after the fact that we had proved the general expression for the PDF obtained by linearly scaling another random variable, continuous random variable. Right? That was the first thing I asked you to think about. The second thing I asked you to think about was y equal g of x, where g is a monotone function. Let's go through that together. So let's assume that y is equal to g of x. X is a random variable. A continuous random variable with a PDF fx of x. And we'll additionally assume that the function g is monotone. What does that mean? It's either decreasing or increasing. Additionally, we'll assume that g is differentiable and the derivative exists everywhere. Okay? So let's think about this case. G is monotone and differentiable. So it's going to look like, this is x, this is g of x. It's going to look like either something like this, an increasing function of x, or a decreasing function of x. The way I've drawn them, they kind of appear linear. If you want let's change the slope a little bit, and let's make it this decreasing one. Arbitrary monotone functions. Since they are monotone, what do we know about them? They are invertible, right? What does invertible mean? So x is mapped to g of x. If you give me a y here, it's mapped to a unique value of x. I can represent this with the inverse function, right? G inverse of y. Okay? So invertible means x, if x is mapped to g of x, then g of x is mapped to the g inverse of g of x. Okay? So let me call this inverse function h. So h of y, or h of g of x gives me x, right? H of g of x. So I go from x to g of x, which is y, and then y is mapped under the inverse mapping back to x. Okay? A lot of ways of saying the same thing. Anyway, so in this monotone increasing case, it's invertible. In this monotone decreasing case, again, it's invertible. So that's going to make it easy for us to write the PDF of y compactly in terms of the PDF of x. Let's try how we might do that. As I said, our general procedure always starts from finding the CDF, Fy of y, which is the probability that y is less than or equal to y, right? What do I do next? I look at this event. What is this event? It is the event that the random variable y is less than a certain value. But what is the random variable y? That is nothing but g of x. G of x is less than or equal to y. G of x less than or equal to y. G of x less than or equal to a certain level implies, in our example, in this monotone increasing example, that x itself is less than or equal to h of that value, y. So, in other words, g inverse of y. So the probability that g of x is less than or equal to y is the same as the probability that x is less than or equal to g inverse of y. Any problem here? This is the, maybe separate this into two cases. This is case 1, the monotone increasing case. This is case 2, monotone decreasing case. And this is true in case 1. In case 2, what is this probability? The probability that g of x is below a value y corresponds to x being bigger than g inverse of y, right? This time it's the probability that x is bigger than or equal to g inverse of y. Any problem? Trivial, right? Okay, so now let's notice that this is nothing but the cumulative distribution function fx evaluated at g inverse of y, and the other one is 1 minus fx g inverse of y, since x is fully continuous and the function is continuous. And now let's find fy of y by differentiating. Fy of y is then the derivative of this in case 1 and the derivative of this in case 2. Differentiate this, what do we get? We differentiate the function. We go from big x, big fx to small fx. Fx of g inverse of y. But we also need to multiply this with the derivative of the inside. Okay? Times the derivative of g inverse. The derivative of g inverse is exactly the same thing as 1 over the derivative of g. Right? So I can multiply this by 1 over the derivative of g, let's call it g prime. In the other case, again, I have a negative sign coming from here. Okay, I have a negative sign, fx of g inverse of y, and again, I have 1 over the derivative of g. There's one thing left to notice to make this expression more compact. In the monotone case, the derivative of g is negative or positive. It's positive in the increasing case, right? In the increasing case, the derivative of g is positive, so g derivative is positive. Here, g derivative is always negative. So in general, this is always positive. This is always negative. So what I can do is I can use an absolute value here and an absolute value here by getting rid of this negative sign. Right? Which gives me the same expression repeated twice, which I can reduce to one final expression. Let me write it here. Fy of y is 1 over g derivative at y times fx of g inverse of y. So exactly. So I have a value y. Example. Okay, example. X is my well, okay, here's an example. Y is 180 over x. We did this example last time, remember? I have the PDF of x, okay? And I want to find the PDF of y. For example, I want to find the PDF of y at the value y equals 6. All right? Now, how I would use this is y is 6, right? And what is the derivative of the function at the value y, which is 6? What is the derivative of this function? Negative 180 over x squared, right? Plug in 6 for the value x. In this case, it would be negative 180 divided by 6 squared, of course, in absolute value. And then here, basically, plug in G inverse of y. When y is 6, what is G inverse of y? Y is 6. What is G inverse of y? 30. Okay? So this would be fx of 30. So maybe it's worthwhile writing this here for the example. So in the example where y is 180, let me write it here. Y is 180 over x. Okay. F, let me write it here, maybe here. F y of y is equal to, what is the derivative? 1 over 180 over y squared in absolute value, okay, times fx of, what is G inverse? 180. Well, in this case, the inverse function looks like the function itself over y. Okay. By the way, if you look here, this is 1 over G inverse of y. If you're working here with the inverse function, G inverse, I'm sorry, this is 1 over G derivative. I could have written here the derivative of, let me not write that to prevent confusion. The derivative of the inverse function could be here to multiply fx of g derivative of y. Anyway, I think this is enough for this derivation. Let's do the general case where the function is not necessarily invertible. It's not necessarily monotone. I'll go through that really quickly. There's a general formula when the function is not invertible and has multiple roots. I don't think you'll ever need it, but let's do it for completeness. Okay, so in this case, I have y equals g of x, and the function g is not invertible. So, for the sake of example, consider this function. So at this particular value of y, think of this value y, there are, in this case, 3 roots. x1 corresponds to this value y, x2, and x3. Now the question is, given the PDF of x, find the PDF of y. Now, I'm curious about y being in this interval. Actually, the PDF at this point. Okay, remember that I have an approximation for the value of y between this value small y to small y plus delta as roughly being equal to delta times fy of y, right? You all remember this expression. I'm going to use this approximation to make you an argument for this conversion, okay, for this derived distribution. So suppose this is y plus delta, okay? Now, the probability that y is between, in this window from y to y plus delta corresponds to x being where? X is either here, right? Because this region corresponds to this region under the mapping, right? These values of x are mapped to these values of y. Also, let me sketch this. These values of x are mapped to these values of y. And finally, these values of x are mapped to these values of y. Okay? So let x1, x2, xn be the roots of the equation f of x g of x equals y. In this case, at this value of y, given y, I have 3 roots. Okay, so let's do everything for 3 roots. Okay. So this probability is equal to the probability that x is between x1 and x1 plus delta 1. Why do I use delta 1? Delta 1 is distinct from delta because the length of this interval is in general different from the length of this interval, right? And the ratio of the length depends on what? The slope, exactly, of g at that point. Very nice. So let me continue writing the probabilities. The probability that x is between x2 minus delta 2 to x2 plus the probability that x is between x3 to x3 plus delta 3. Okay, now we'll write everything in terms of this approximation. Delta times fy of y is roughly equal to, this approximation goes better, of course, as the interval delta is made smaller, delta 1 times fx of x1 plus delta 2 times fx of x2 plus delta 3 times fx of x3. Did I forget something? Excuse me? X is between x2 minus delta 2 to x2. Why not?
x2 minus delta 2.
Doesn't really matter because delta is small. But you're right. Right. It doesn't really matter. So because the idea is I'm assuming that the PDF is roughly constant in this interval from x1 to x1 plus 2. That's the whole point, right? But you're right, in principle. Now, so it's fine as long as you believe this approximation, which you should believe it because it becomes true in the limit. So now, all we need is divide by delta. So divide by delta everywhere. and we get fy of y. Now, what is the ratio delta 1 over delta? The slope. So the ratio of this to this. Now, the ratio of delta to delta 1 is exactly the slope of g. So this is 1 over the slope of g at which point? At x, 1. Right, right. So this is 1 over the derivative of g at that point. Times fx of x1 plus 1 over the derivative of x2. What do you think? No, because the derivative of x2 is negative at this point. So this is negative 1 over the derivative of x2. But I can use an absolute value to correct that. Okay, fx of x2 plus, similarly, 1 over the absolute value of g derivative at x3. So let me use an absolute value here as well. It's positive. So in general, if I want to, if x1, x2, xn are the roots of this equation, g of x equals y, I can write fy of y as the summation, right, 1 over absolute value g inverse, g derivative of xi times fx of xi. Okay. Right. So basically this was the negative of g prime, where g prime is itself negative. No. See, okay. It's a ratio between lengths. It's always positive. Look, this after all is a probability term. It's a probability. So you know it has to be positive. The ratio of this probability, the ratio of this length to this length, okay, must be positive because it's a ratio of distances or lengths. Okay? If I want to express this ratio in terms of the derivative of the function, when the derivative of the function is negative, I simply take the negative of that negative, which is equivalent to using absolute value. I asked you to think about this. It was your homework. So, anyway. By the way, if you look at this expression, okay, so this is over xi such that g of xi equals y. So let me write this. Let me put this in a box. Now, do you realize now that we have a typo in the first one, in the first case, the monotonic case? We made a mistake when writing the monotonic case. So remember the invertible case or monotonic case, meaning g of x equals y has a unique root, g inverse of y. Let me write this using this general expression. F y of y equals what? 1 over g inverse at x, right? What is x? G inverse of y times fx evaluated at g inverse of y. Okay? So please correct this in your notes if you took notes. Okay, this is the end of the story. As I said in the beginning, this is not anything that you would absolutely need to use, because in general, we have a procedure, a very simple procedure going from first principles to find the derived distribution. What do? Let me repeat. First, we find the CDF of the new random variable, the probability that y is equal to less than or equal to y. And then we differentiate it, if it is differentiable. Okay? So this is something extra, if you will. Yes, please.
Bu fonksiyonun tersi negatif değerler de oluyor. O zaman saçma bir şey olmuyor.
What do you mean?
Yani negatif değerler de oluyor. Tersi de negatif değerler. Ya tersi ilk fonksiyonu y değerleri hep pozitif. X değerleri negatif.
No. That's y is only positive in this example. It's for the sake of example. It could have been different. Okay, here's the function, and I look at this value, y.
Peki o
Why
zaman
not?
anlamı ne oluyor ki negatif olunca?
I don't really, nothing here, nothing we did here is specific to the sign of y. Nothing changes. Okay, think about it. It would be a useful exercise with PDFs. Okay, it's not the nicest formula in the world. Okay, so let's continue. Last time, we started talking about functions of multiple random variables. And if you remember, we looked at this example. This was the last thing that we did. X and y are uniformly distributed 0 to 1, and they are independent. And we computed the PDF of their product, x times y. Do you remember what it turned out to be? The PDF of the product. The product, where does it live? It lives in the range 0 to 1, just like x and y themselves. But we found that the product is very different from uniformly distributed. Fz of z looked like this. It was equal to negative logarithm of z wherever z is between 0 and 1. Okay? And I think that was remarkable and interesting. And I advised you to not confuse Fz of z, which is the PDF of x times y, with the joint PDF fxy. We use the joint PDF fxy, in fact, to compute this. Let's continue with another example on the same topic. Let's see. Okay, yes, the computer went to sleep. Okay, it's back now. Okay, a very important topic is next. What happens when you add two independent random variables? This is one of the cornerstones of this class because it leads to a very important conclusion, a very important general theorem, which is the central limit theorem. Let's start from basics. So I have the random variable x, and I'm adding to this an independent random variable y. I don't care about the distributions of these random variables, and I let z be the sum. Okay? For the case of, for the sake of example, suppose x and y are discrete. Okay? X and y are discrete random variables, and they are independent. Okay? I want to write down the probability mass function of z, pz of k, if you want, pz of k, in terms of the probability mass functions of x and y. Pz of k is nothing but the probability that z is equal to k, okay, which is the probability that x plus y is equal to k. So, to find Pz of k, I need to be able to compute the probability that x plus y is equal to k. How do I do this? I know the distribution of x and I know the distribution of y. Maybe I can make the total probability theorem come to my rescue again. How do we do that? Well, condition on different values of x, for example. The probability that x plus y sum to k, given x is equal to, I don't know, L, times the probability that x is equal to L, which is nothing but px of L. Okay? Now tell me, what is the range of L in the summation? In general, if they're allowed to take any real value, the support of the random variables are not necessarily restricted, I can let L be negative infinity to infinity, right? This will always be true. You see this? This says that I don't care what px of L is, what px is. I sum over any possible value that x can take the probability that x plus y equals k given x is L. Of course, I weight that by the probability. Why not? Let's do that. Okay, good. So I can also, you tell me. K given, for example, y equals, again, L. Let's use m, okay. M, py of m. M goes from negative infinity to infinity. Okay. Now what is next? I can write this. Now x is given, okay? X is given. So x here is not a random variable anymore. It's a value, L. It's equal to L. So I can write this as y equals k minus L, given x is equal to L, px of L, right? Any problems? I can do the same here if you want. M from negative infinity to infinity, px is equal to y, x is equal to k minus m, given y is m, py of m. Now what's next? Very important step. I will use the fact that the two random variables are independent. Since they're independent, y doesn't care that x is equal to L. Okay? The probability that y is equal to k minus L is fixed regardless of this event in the conditioning. So the conditioning can be dropped. So let me write here independence. Because of independence, we drop the conditioning to say the probability that y is equal to k minus L times px of L. But what is this? This is py of k minus L. So finally, I reach the point where I can notice that this has a special form which I call the convolution of the PMFs, Py and Px. This is the convolution of Py and Px. In other words, Py of k convolved by Px of k. On this side, the point I would reach would be, similarly, summation m going from negative infinity to infinity, Px of k minus m, Py of m. It is exactly equal to the left-hand side. So both expressions give me the convolution of the PMFs. I believe all of you know about convolution, and all of you have done examples of convolution, so there's no surprise here. It's not a new expression for you. But I think it is new in terms of probability, its occurrence and probability. It is interesting that when you add two independent random variables, their PMFs are convolved. You know what convolution does from earlier courses. If you have two functions and you convolve them, this support spreads out. Okay, we'll see that on examples. Let's do the continuous case next. Let's do the continuous case real quick before we give a break. So in this case, x and y are continuous random variables. And we add them. We'll use the fact that they are independent. Okay? So let's think about the PDF of the sum z. Okay, let's think about we want to find the PDF of z. It's always safe to start with the CDF. Okay? F z of z is equal to the probability that z is less than or equal to z, which is the probability that x plus y is less than or equal to z. Okay? What I'll do is, again, I'll use the total probability theorem. This time, I'll write this as an integral. Okay? This is the probability that x plus y is less than or equal to z, given, in analogy to this, given that x takes the value x times fx of x. What is the range of integration? In general, I don't care about, if I don't care about the density and I left it as a function, this expression, this integration will go from negative infinity to positive infinity. Okay? Any problem with this? So what do you suggest we do next? what do we do next? I can express this probability as the probability that y is less than or equal to z minus x, because the value of x is given to be small x. Okay? And I can also drop the conditioning because of independence. Shall I do those at just one step? Okay, let's just drop the conditioning because of independence. So I'm going to say again by independence. And I have fx of x dx. Okay. Now, what is this expression? That is nothing but the CDF of y. Right? So that is fy of z minus x times fx of x dx. Very nice. What is this thing that I computed? It's the CDF of z. So the PDF of z is d by dz of the CDF, which I just computed. I need to differentiate this integral. Since the integral converges, I can switch the order of integration with differentiation. So I have d by dz fy of z minus x fx of x dx. Okay? D by dz fy of z minus x, what is that? The derivative of this function is fy of y, small fy of y, and this is small fy of z minus x times the derivative of the inside, which is 1 in this case. Okay, so what did I find? Let me write it here. F z of z is integral from negative infinity to infinity. Fy of z minus x, fx of x dx. What is this? You know this very well. This is a continuous convolution. Convolution. The notation we have is fz of z. Let me write it here. Fz of z is equal to fy of z convolved by fx of z. This is a notation for convolution. Convolution is a very fundamental thing in signals and systems theory, and it has a very special place in probability as well. So next, we'll see two examples of convolution which will get us almost to a very important theorem in probability, which is the central limit theorem. Let's now give a break.